So let me just tell you a little bit about myself. So I am a theoretical physicist, and my training during my PhD and my early career years have all been in cosmology and high energy physics, big questions related to the Big Bang and black holes and that sort of stuff. However, I always connected the origin of the universe with the other origins that we think about, like the origin of life and also the origin of consciousness. And a few years back, I became very interested in the question of the origin of life and what science could say about that, of course, from a physicist's perspective, right? So I wasn't doing geochemistry, I wasn't doing planetary science or exoplanetary astronomy. I wanted to find out what being a physicist could help with the understanding of the origin of life. And so one of the questions that got me in there was actually a question that Abdus Salam, whom you may know was a Nobel Prize winner who shared with two other guys that unified the electromagnetic and the weak interactions in the so-called electroweak theory of particle physics. He was actually one that wrote a paper where he tried to understand if the weak interactions, the ones responsible for um, radioactive decay, had anything to do with the origin of life. And his reasoning was the following. He thought that, as you know, in particle physics, there is a very fundamental asymmetry of nature, which is that, in a nutshell, that neutrinos are left-handed, right? So particles with spin a half, they can spin into the left or they can spin to the right, so to speak, and they can have something called a helicity. And it turns out that the neutrino is very particular, in which it only likes to go one way. And we call it a left-handed particle. And so there's this fundamental asymmetry in nature, which is very important. And Salam conjectured with other people before him that perhaps, since there is a fundamental asymmetry at the nuclear level, perhaps this asymmetry could be amplified somehow and have something to do with the asymmetry we find in life. Now, what asymmetry is that? So, to answer one of Adam Smith's question here, it's what we call homochirality, right? So the idea is the following. Chiral comes from the word Greek, in Greek called hand, right? And you know very well that if you try to use your right hand and you put a left glove in your right hand, it's not going to work, right? So you cannot superimpose your hands on one another. And that's what chirality is about, is that your left hand is the reflection of the right hand, right? And it turns out that many of the molecules that make up the design of living creatures, from the amino acids that appear in proteins to the sugars that appear in RNA and DNA, they can be chiral, which means the following. They're made of, if you can picture this, they're made of a center. So there is like a center, which is a carbon center like this. And you can imagine four legs sprouting out of this. And if these four legs are different from one another, that means the carbon is related to different radicals. It turns out that those molecules can have chirality. That is, if you switch the order of a couple of these things, one becomes the mirror image of the other. So that's the idea of chirality in organic chemistry. And it was Pasteur in the 19th century that discovered that that the molecules that have to do with life seem to have a very odd property to them, which is that if you synthesize them in the laboratory, you get a 50-50 mixture of left and right-handed, let's call it left and right-handed molecules. And it turns out that when you synthesize them in the laboratory, they come out as 50-50, but when you find them in living creatures, they're always of one specific chirality. And hence the homochirality, meaning the choice of a single chirality in living things. So the question is, what in the origin of life caused that asymmetry, right? And so there was this connection with weak interactions, and that's how my past as a particle physicist and my interest in the origin of life came together, and I started to look into this question. In fact, with one of the organizers of Sagan Live, which is SAGANet, which is Sarah Walker, and we figured out that in order to answer this question, as in fact is true of any other question in the origin of life, you have to take into account the effects of the environment. Okay, so we've done a lot of research on how the question of chirality relates to the different environments that could have occurred here on early Earth. But I see some other questions here. I see there is one here from Poppy that says, you mentioned you have your roots in studying the Big Bang. What is your take on the different theory that the universe was spawned from a hyper black hole? Wow, that is a pretty crazy theory. I think it should be actually the other way around. I mean, if you could think of the Big Bang as an event, then you would really think of it not as a black hole, but as a white hole, in the sense that what you see there is not matter falling in, which is what you see in a black hole, but matter coming out of a very small region of space-time, right? So that's more what I would consider a better analogy. Now, what you can say is that perhaps our universe is not the only universe out there, that is part of a giant multiverse. And in that multiverse, you may have a lot of failed experiments. That means universes that may not be able to expand and grow, but they actually can collapse. And if that happens, they could become black holes in a sense. And, you know, I like to question a lot of things. And since nobody has asked a question about what I've been writing lately, let me just say something about it, which is, since we're all discussing the origin of life and questions related to life in other planets, it's very important to put in context, what do you mean by life? And what do you mean by origin of life here or elsewhere, right? And so one of the fundamental questions, and I would like to say perhaps a little provocatively that it's a very important one, is that we will never figure out how life started here on Earth. Now, that doesn't mean that we can't figure out how life starts, but unless someone can prove a theorem that shows that there is only a very specific metabolic pathway for life, or if not one, very few possible metabolic pathways for life, then life here is a complete unknowable, in the sense that you can try to reconstruct possible ways in which life may appear, but you can never really trace that down to what we know of early Earth, because our knowledge of early Earth is going to be necessarily incomplete, because you can't take a time machine and go back exactly and reproduce the conditions here. So, and because the conditions, the environmental conditions, are so essential for the origin of life, then that tells you that even if you're able to create life in the laboratory, that life that you created in the laboratory will not be the way life appeared here on Earth. So I have another question here. They look like they're all ranging around works in unification and things like that, which is perfectly fine. So Adam here is asking how important it is to engage with the public. And that's a very pertinent question, because very recently there was a study from Nature that talked about how scientists do not mostly engage with the media and with the public, mostly because they are suspicious of how to do that, right? And on the other hand, a lot of them recognize that you do need to engage with the public, simply because, well, there are several reasons, right? One obvious reason is that it is the public that is funding our research, and because of that, we owe it to the public to explain why our research is relevant, right? So we want to make sure that what we say and why we're saying it, and the money that we need to keep on asking questions about nature, is understood as a very important need for society, right? So that's one very important answer. The second reason why it's important to engage is that science is part of our culture, right? It is really how we understand the world. And the way we understand the world is very much part of who we are and how we understand ourselves in the big context of things, and even within society and smaller groups of cultures. So science, in a sense, is an integral part of our culture, of our way of thinking about who we are. And for that very reason, to not share what's going on with science is sort of like creating a kind of secret society that has all this knowledge that is not willing to share. And that's really not what science is about, right? Because one of the things which is really essential about science is that it is a truly democratic activity, and that what we know is really something we should be sharing with a lot of people. The third reason for sharing and discussing science with the general public is that we want to make sure that we inspire the younger generation to become our colleagues, right? And so the best way to do that is to keep on telling this wonderful story about the world that is a story that we can only tell with the tools from science. Okay, CB is asking me a question about the 11 dimensions of the universe. What does it mean, actually? Well, so the idea there is the following, is that if you believe that all four forces of nature should be unified in a single force, then the best candidate for that theory at this point is called superstring theory, as you probably know. And superstring theories mathematically can only be formulated in 10 or 11 dimensions, right? So you have to take one out for time. So we are talking about either 9 or 10 spatial dimensions. And the question is this, do you agree with that? Or what does it mean? Well, in a sense, in science, it's a matter not of agreeing, but we're finding compelling evidence, right? And I did my work on 11-dimensional theories for a long time. That was actually my PhD topic. And the idea there, of course, was very fascinating, which is, wow, can we actually come up with a theory that can put all the forces of nature together? That would be awesome. And that was in the 80s, right? And of course, this idea is from the 70s. And here we are in 2015. And a lot of the premises that make this possibility realistic have not been verified, right? So one of them is the super from superstrings, which has to do with supersymmetry. That's a theory that tells you that the two fundamental particles of nature, bosons and fermions, the particles of matter and the particles that transmit the forces between particles of matter, can actually be rotated into one another. So supersymmetry, right? And makes lots of predictions. And so far we haven't verified any of them. A lot of expectancy right now with the LHC, because maybe, lots of people hope and believe that the LHC is going to see something related to supersymmetry. We'll have to find out. And of course, the extra dimensions is the same deal, right? I mean, we need to be able to have some empirical validation for these ideas, and we have not, right? So that's the practical aspect of unification and 11 dimensions, etc. Now, there is a philosophical aspect to this question, which is also extremely important. And the question is the following, is can we actually say that we are able to construct a complete theory of the way we understand nature, right? And by doing that, I'm talking about understanding nature only from an elementary physics perspective, that is, with all the forces of nature unified as a single force. And the answer to that question is no, we cannot, because all we can do is gather information about nature the best possible way, right? That's what we do. We gather information, we develop models, and we create descriptions of the natural world to try to make sense of what's going on. And this process, which is pretty much the way science functions, right, is necessarily a process which is incomplete. It is incomplete because we can only gather so much information from nature through our tools, and our tools have limits, they have ranges, they have they have accuracies and precision limits, and because of that, there is only so much that we can actually see out there, which basically means the following. It means that even if we think we can build a theory that unifies knowledge, that theory that unifies knowledge is knowledge as we see it now. Is never a final theory of knowledge, because a few years down the line, we should be able to find other things which are not part of this theory and that should be incorporated into it that may change it in very radical ways. So I think it takes a lot of humility to understand and make sense of theories of knowledge in that sense, to kind of know that there's only so much we can say about the world and not to have these sort of illusions of grandeur that we can actually make sense of it all, which actually makes everything much more exciting, right? Because you don't want to answer all the big questions. You want them to be open questions, so you keep on searching. Okay, Sarah is asking me if I think that life and consciousness have the same physics. That's a very difficult question. I mean, in a very fundamental sense, we're all a bunch of atoms, right? I mean, that's essentially what we are. We are a bunch of atoms connected to one another, making into molecular machines, and these molecular machines can have metabolic functions, and they eventually become complex enough to become multicellular, and those multicellular beings, some of them become somewhat intelligent, and on the top of this chain, at least here on this planet, here we are, right? So in a sense, we are molecular machines capable of self-awareness. So if you take that perspective, then yes, all there is physics, right? I mean, and then, of course, chemistry and biology are just different levels of material organization, but that's all there is to it. So yes, I think that from that perspective, mind and consciousness and life are all the same stuff, right? However, that does not mean that the stuff we are made of can understand the stuff that thinks. And what I mean by that is the following, is that even though the brain is ultimately a bunch of neurons and the neurons and synapses are ultimately a bunch of molecules, that does not mean that we, capable beings as we are able to actually make sense of what consciousness really is, right? And there's a big debate in philosophy right now, and there are there are people saying, of course we can, it's all matter, we're going to figure everything out, just give it time. And others that call this the hard problem of consciousness, that say, look, that is too simplistic an approach, the mind cannot figure itself out, right? And I have to say, I have a lot of sympathy for the second team, the hard problem of consciousness team. Sometimes they're called the new Mysterians, because it is very possible that even though we may be able to explain what goes on in your brain when you're in love, or what goes on in your brain when you're thinking some thoughts or listening to music, that is a very different problem from explaining the subjective experience of being in love or listening to a song. And it is this subjective experience that is the way all this chemistry, all these flowing neurotransmitters become a feeling that is the big mystery. So you may be able to even simulate and put the right neuro simulators or stimulators in your brain and take some drugs and be in love, and people already do that, right? But that does not explain the sensation of loving. And that perhaps is what's really hard about this problem of consciousness. And that's the question. James Brown asked me for homochirality, and we already did that, James. I think you came in a little late. I'm really sorry. So let me move down here to some other possible questions there. Oops. Whoa. Let me see. There was something about the LHC, but somehow I managed to... Whoa, why are all my windows disappearing? Hold on a second. I am trying, I'm sorry guys, I'm trying to figure out what happened to my questions here. They somehow disappeared, and I do not know exactly how to bring them back up. So let me see if they are perhaps behind my screen. Um, I'm trying to figure out where my questions are. I'm sorry, guys. I do not see it. It looks like you can see me, but I cannot see your questions. Sarah, if you're still there, could you perhaps retype some of the questions in your private feed to me? If you're still there. Okay, I think I got something here. Okay, so yes, Jacob asked me about the LHC. Do you think there is a real risk of large particle accelerators going haywire and destroy the universe? No, Jacob, there is no such risk at all. People have looked into that in great detail, and they did not find any risk whatsoever. In fact, it turns out that it turns out that it turns out that the cosmic rays that come out from the sky have much more energy than what's going on at the LHC, and they've been coming out for billions of years, and we're still around. So there's really almost zero chance that something like that would happen. So CB is asking if it is possible for me to take up a PhD in astrobiology, having a background in electronics engineering. Wow. That's a tough one. I think you, from space engineering, you could definitely steer your career towards instrumentation related to astrobiology research. So that would perhaps be a way of getting into the field. You know, you can possibly do that, and so you'd have to kind of make sure that you have to just make sure that you stick along groups that are interested in doing space research related to astrobiology, which there are lots of them. Yeah, Jacob, you're welcome. So you should not worry about scientists creating the end of the world. You know, that's not going to happen, as far at least not this way, anyways. So that's a good thing. Um, I assume you're all seeing me loud and you're seeing me and hearing me loud and clear, correct? All right, so now I need more questions. If I don't have any more questions, I can perhaps probe you and ask you guys, where are you coming from and what do you want, why are you interested in astrobiology? Perhaps we can have a little real conversation. Yeah, I see the questions, but I think I answered all of them. Okay, I see that there are new questions coming up. So, Yeah, definitely. Vicenta is asking if biophysics is a good route for some. Absolutely, biophysics is an excellent route for many reasons. First, because you know more biology than most physicists, okay, and that's a major. And the other one is that a lot of biophysics research has to do with membranes. You know how there is transport across cellular membranes, and this is a very important question related to the origin of life, for example. Like, do we need an entity which is isolated from its environment by a semi-permeable membrane in order for life to develop? So that will be a very interesting, a very important question. David Deamer, for example, in California, is one that is very interested in that sort of question. So absolutely, biophysics is definitely a way to get into astrobiology. There's a question from Poppy regarding the Fermi paradox. Is there a reason for extraterrestrial life not to have made contact that you believe makes the most sense? That's an excellent question. And I think there are two reasons for that to happen. Okay. The first reason is that I think that intelligent life is extremely rare. I think it's there. We cannot rule things out. Remember, we can't use science to rule something out as long as it obeys the laws of nature, and intelligent life, as far as we know, obeys the laws of nature. But we can say that, at least from our history here on Earth, there are so many steps that life has to go through, from very simple prokaryotic cells to eukaryotic cells, to more complex cells, to beings that have different organs, to beings that think. Each one of these jumps is so complex, and it depends so much on the environment and on the relationship between the planetary environment and how life is developing here, the composition of the atmospheres, of the oceans, that quite possibly, at least I would say so, with my own opinion, intelligent life, if it exists elsewhere, is going to be very rare. So that's one of the reasons why it hasn't been here. The other reason is the distances, right? I mean, we're talking huge distances, and Fermi's paradox basically saying that, if you live in a galaxy which is 100,000 light years across, right, and is about 10 billion years old, if you had a civilization a million or 10 million years before we appeared, which is nothing in billions of years, they would have had plenty of time to colonize the whole galaxy. So where are they? So that's the Fermi paradox. And perhaps the reason is simply one of interstellar distance traveling, because it's not just that the distances are huge. Let me just give you an example. If you picked up the fastest rocket ship that we have right now, and we try to go to Alpha Centauri, which is just our next nearest neighbor at 4.5 light years away from us, so just around the corner, that would take us over 100,000 years, right? So these ETs, they may have developed amazingly fast ways of traveling through space, but even if you travel at a tenth of the speed of light, a trip from Alpha Centauri to here would take 45 years, right? So the question is, why would they come here? Is there really an intent? And that's a psychological question that has to do with perhaps they're not interested, or perhaps they have been here, or perhaps we are their creation, right? So there are all sorts of interesting possibilities. But I think, to me, the most fundamental one is the rarity of intelligent life in our galaxy. Sanjoy is asking, when did consciousness first came to be in the evolution of life? Well, again, that is a difficult question because it depends on how you define consciousness, right? So people working in the cognitive neurosciences, there is a whole range of definitions of consciousness, and they would say that a thermostat is conscious, that it has a level of consciousness, which honestly, in my opinion, is kind of bogus, but they use that to quantify this gradation of consciousness, right? So the question then becomes, if you go and look at the evolution of life on Earth, when did complex life became conscious. And if you mean human consciousness, then we know, right? But the Neanderthals were here before us, and they were conscious. So it is quite possible that, sorry, I had a call here. It's quite possible that they had some level of consciousness. So really, we do not know, right? We do not know the answer to that question. Okay, so so what advice do I have for people with an interest in astrobiology? Well, there are many ways you can go through this. Right now, if you're an undergraduate, what you could do is you could do either physics or biology or earth sciences as your major, and make sure that you have enough courses on areas of interest for astrobiology. So astronomy, genetics, perhaps even information theory if you want to do more theory. And then you really get serious about this at your PhD level. Then you make sure you go to a school where there is an astrobiology program. So before you apply, you find out where to do that by going to the website, looking at the faculty members, and seeing what kind of research they are doing, and then saying, yeah, I really want to go there, and then apply there. And from there, you move on, right? There is the NASA Astrobiology Institute, the NAI, which is something that you should all be looking at as well for information on conferences at the undergraduate level, at the graduate level. It's a great resource for everybody. Oh, somebody's asking me, Poppy's asking me, what are my thoughts on the universe potentially being a simulation, right? That's a great question. In fact, I wrote a book called The Island of Knowledge that came out last year, and it's really about the nature of reality. So basically, the fundamental question of the book is, how do we know what is real, okay? And of course, this issue of simulation is fundamental to all of that, right? Because if we live in a simulation that is like the Matrix, right? So we are not really autonomous beings, but we are really part of a big scheme where our brains are being fed this information, but we actually in some sort of a capsule somewhere. Or even more, if we are characters in a video game, right? And this video game is being played by other intelligences, just like we play The Sims. So imagine an intelligent version of The Sims, and the characters in The Sims think that they are autonomous individuals, and they are not because they're being played by other intelligences. So can we tell if we are members of a simulation or not? And that's a very disturbing thought, right? Because to most people, if we are part of a simulation, that means that we are not free, right? And it has to do with freedom. However, you can also argue that, you know what, if I don't know about it, and if I feel free, and free will is a whole other discussion that we can have, but if you feel free, then does it make any difference, right, or not? So my thoughts is that the universe could not be a simulation, because in order to simulate the universe, you'd have to have a machine that would have to have all the information gathered in the universe, or most of it, and be able to simulate itself. And in computer science, you know that you cannot simulate yourself. A machine cannot simulate itself, which has something to do with the brain not being able to perhaps understand the mind, right? But so I don't think the universe is a simulation, but I could imagine that you could create very complex virtual realities where you could fool people into believing that they're living their lives when they're actually part of a giant simulation. Now, are we part of this or not? Nobody knows, right? If you look at Nick Bostrom's essay, do we live in a simulation? One of his answers, which I think is my favorite, is that those intelligences have no interest in playing that sort of games, and I would hope that an intelligence that is sophisticated enough to create a simulation which is sophisticated enough to create what we see around us have better things to do than playing this sort of video games. I mean, they have done all these experiments already. So somebody's asking me, CB is asking if I deal with Eastern mysticism and yogis while doing works on consciousness, are they irrelevant? I would say that I don't think they are irrelevant if they're serious. There are lots of very important cognitive neuroscience research right now being done on meditation. In fact, I think it was the cover of Scientific American a few months ago, and it was a team of a very important person from the meditation community and a monk and cognitive neuroscientists trying to figure out what sort of relationship and what sort of processes in the brain are triggered by serious meditation, and if meditation is healthy and if it benefits people. And the general consensus seems to be that yes, absolutely, that meditation does seem to benefit the brain and your powers of concentration and your overall health. So I think that's fine. It's when things become pseudoscience that you have to worry about, right? When you start talking about weird things like quantum healing and other crystals and all that kind of nonsense, then you have to watch it. But otherwise, there's a lot of very important research being done right now that goes beyond not just meditation, but beyond traditional medicine. And I think this is all very good. Andrew is asking if truly intelligent robots will understand that they evolved from us and treat us nicely for our advantage in evolutionary terms. I wish that were true, but I have to say that we are not like that. Just think about it. I just read the other day that there are only 900 mountain gorillas left in the world. 900, right? And they're being killed because people want their paws or they want their fingers or they want whatever. And this poaching is completely inhumane and it's stupid to an extreme because the species is almost extinct. And we evolved from them, right? We evolved with them. We have a less common ancestor that we share with the mountain gorillas, that we share with the chimpanzee, that we share with the orangutan. So these guys are all our cousins, and unfortunately we don't treat them that way. In fact, their survival right now, the survival of the mountain gorillas, depend completely on us. We could go there with a bunch of machine guns and wipe the species out of existence. So I don't think that the robots, knowing that they came from us, would treat us with any more respect than we are treating the species, other species around us, right? What you have a distribution of mindsets, a distribution of morals, and it is very hard to imagine that intelligent robots will have any more, although I would love to believe it's true, realistically, I think we have to be extremely careful because that may not be true. They do not necessarily will be more moral than we are, right? However, there's another way of thinking about that, which is it's not going to be just robots out there, but it is our species as a whole that is going to evolve as it combines with all this new technology. So instead of saying that, the robots are going to kill us, perhaps we are going to become the new robots. So we are going to become this new bio-cybernetic entities, which are a mix of biology and a mix of silicon technology, and we are going to become something else and hopefully something better. Sanjoy, is there anything you would have done differently when choosing your career path? No, I have to say, perhaps I'm not a very good example, but I have been very privileged in my career that things just worked out, right? So, I finished my undergraduate degree in Rio, so I studied in a school that nobody ever heard of, right? The University of Rio, Federal University of Rio. But then I went to do a PhD in England, and that was the big turnaround, right? Because then I was part of the big brotherhood, so to speak, and became more competitive in the job market with a PhD from there, right? So that made a big difference. So perhaps the only thing that happened in my career, which I sort of regret, is that when I started university, I was very conflicted about doing physics, just because physics in Brazil in the 1980s was sort of like a crazy choice as a career. And so I started doing engineering. and chemical engineering, to be precise. So I did 2 years of chemical engineering before I switched to physics. And if there was anything that I would have done differently, perhaps I would have started physics right from the beginning as opposed to doing 2 years of engineering. But that's just me. I mean, that didn't really affect that much. In fact, it helped me understand my need for doing physics even better. Yeah. Uh, So Sarah is saying, what do I do for hobbies? Well, I do a bunch of different ones, but my two favorite ones are, since I live in New England, in northern New England, where there are lots of rivers and lakes and mountains and trails, I fly fish a lot. And in fact, if you go to Through the Wormhole with Morgan Freeman, actually, if you go to my website, marcelogleiser.com, you're going to see there a clip of Through the Wormhole with Morgan Freeman, with me fly fishing and talking about the limits of knowledge. And the other hobby that I do is I do trail running and obstacle racing. And in fact, when I went to visit Sarah a couple of weeks ago, I was there to give a bunch of talks at Arizona State, but I was also doing a Spartan race, which is my favorite kind of obstacle racing. And so there's another clip from Through the Wormhole with Morgan Freeman where I do a Spartan race. You can see that if you would like to. And it's really not about Spartan racing. It's about, will we be gods? Meaning, how far can you push the human race into perfection? So there's quite a possibility for me to switch to biology from electronics. Yes, you can do that. I don't see why not. In fact, there's this whole thing called what is it called now? It's a new joining of robotics with biology, and that's where you should go and look. How these two things meet, and that's where the answer goes. And of course, that is extremely important for space exploration. If you can create extremely self-sufficient, reliable, and somewhat smart robots for space exploration, that's going to be a main step for astrobiology in the future. So that would be a great way to go. So somebody's asking me about last words of wisdom for young scientists. Yes, definitely. I think there are two important things about becoming a scientist. One is as a student, right? And as a student, we tend to rely way too much on our teachers. And if you're lucky enough to have good teachers, that's great. But often that's not the case. You're going to have not so good teachers. And so you get sort of disappointed and discouraged. And you say, this sucks, I want to move on. And my main advice is the following: do not rely on your teachers to learn. Rely on yourself. So if you're learning about mechanics, or if you're learning about genetics and you have a textbook, go beyond what the textbook is telling you. Be independent, be self-sufficient, be curious, and not passive in the way you acquire knowledge about your field, right? So that's the first important thing. The second important, just one thing about teaching. So if you are going to become a teacher, my best piece of advice is the following: remember everything that you hate about your teachers. Oh, that guy is completely disorganized. She doesn't look at the classroom. They never turn around. The blackboard is a mess. Remember all the things you hate about your teachers and don't repeat them. That makes a big difference for your students in the future, because clearly, if you repeat the same mistakes, then bingo, your teaching is going to not be good as well, right? So that's really something I always tell my students, okay? And finally, on the advice on science, my advice is be bold on your ideas, but also be realistic, at least in the beginning. So don't go too crazy trying to solve all the big problems of the world in your PhD. Learn the fundamental techniques that will give you the tools for you to go and then later on tackle the problems that you really want to work on. It's really a gradual process and takes patience, but there is nothing better than the life of the sciences. I can promise you that. I'm just seeing if there are any other questions so we can wrap this up. All right. Well, I thank you all, folks, too. Let me see if I can. It was a pleasure. It's a lot of fun to do this, and I'm glad there are about 40 people right now in the main room. And anytime you have any questions, you can email me, okay? And you know how to find me, marcelogleiser.com.